Inside the human body, the environment exists in a state of constant aggressive flux. Temperatures swing from freezing to scorching, and resource availability varies wildly. Yet inside a healthy human, variables like core temperature and blood pH stay within a remarkably narrow range. Biologists define this persistent internal stability as homeostasis. The linguistic roots of the term translate from Greek as homeo, meaning same, and stasis, meaning standing. That direct translation misses the complexity of the process. Maintaining internal stability is an active metabolic demand. Staying at a constant internal baseline against an erratic external world requires exhaustive, dynamic work. The body manages these adjustments through engineered feedback mechanisms that continuously monitor and recalibrate internal conditions. To understand human physiology, we have to map the hidden, relentless control loops that counteract external chaos to keep us alive. When an internal change occurs, the body operates like a closed-loop systems processor. Every loop begins with a receptor. This is the system's frontline sensor, designed to detect a specific change or stimulus in the environment. Once the receptor detects a shift, it relays that data to the control center. This processor evaluates the incoming information against the body's set point to determine the necessary action. The control center then signals an effector. This is the physical component, often a muscle or a gland, that executes the biological response. The goal of this three-part communication chain is to return the body to its normal condition. In a true feedback mechanism, a portion of the system's output is routed back to its input. The resulting biological response physically alters the original stimulus that triggered the loop. Survival relies on this three-node communication loop functioning in perfect, uninterrupted sequence. We can see this architecture at work by tracking how the body regulates blood glucose levels. As the sequence here outlines, a spike in blood sugar acts as the stimulus. Receptors in the pancreas detect this excess and notify the control center. The control center then triggers the release of insulin. This hormone acts as the effector, working to reverse the original glucose spike. The final output of the system actively suppresses the initial trigger. By lowering blood sugar back to baseline, the response removes the very stimulus that activated the loop. This suppressive action is known as negative feedback. Most bodily systems rely on this method to maintain a stable internal state. The body maintains survival by constantly dampening any deviation from the physiological baseline. This raises a question. Why would a system designed for stability ever intentionally accelerate a drastic internal shift? The body uses a second control logic known as positive feedback. This mechanism enhances or amplifies the initial change rather than suppressing it. Instead of reversing the stimulus, the effector's response actively increases it. During childbirth, the release of oxytocin stimulates physical contractions, which then trigger the body to release even more oxytocin. Blood clotting follows the same pattern. Damaged vessels attract a few platelets, which release chemicals that pull in hundreds more in a rapid cascade. In this sequence, the response feeds back into the system to drive an even greater stimulus, creating an upward amplification curve. Positive feedback loops provide a temporary override, driving finite events, like sealing a wound or delivering a child, to a rapid conclusion. While corrective loops maintain daily internal peace, these amplification loops are the specific protocols required to resolve physiological emergencies. Because these mechanisms rely on precise data flow, a severed feedback loop has immediate consequences. We can use the glucose homeostasis model to see how a single break in the circuit destabilizes the system. If the signal from the control center is blocked, or the effector fails to respond, the communication chain is broken. Without the suppressive response from the effector, the initial stimulus of high blood sugar remains uncorrected and spirals out of control. This specific failure of the glucose feedback loop is known clinically as diabetes mellitus. This condition illustrates that many pathologies are, at their root, a structural breakdown in internal systems engineering. These feedback loops provide the specific architectural logic that preserves internal stability. When the communication remains unbroken, the body maintains the conditions necessary for survival.